Hi everyone, so this is me doing the examples for chapter 11.2 of the year 1 statistics and mechanics book. This is on using differentiation in variable acceleration problems, and in chapter 11.1 we did lots of work with functions of time, so where we had velocity functions, acceleration functions and displacement functions that were time dependent, and we had to find various things, so the kind of maximum speeds, the greatest distance travelled, that kind of thing, when an object was instantaneously at rest, and lots of those skills we'll use in this subchapter. So just to make a couple of notes first. This is just a kind of reminder to us that velocity is, by definition, the rate of change of displacement. So that is how fast our velocity is changing, or how much our velocity is changing every second. And we know from working with velocity time graphs a lot that that velocity, and with distance time graphs and displacement time graphs, that velocity is found, or can be found, by calculating the gradient of a displacement time graph. And we know that gradients are related to differentiation, so we'll come on to that in a second. And then the second thing is about acceleration. By definition, acceleration is the rate of change of velocity so that is by how much our velocity is changing every second. That is our acceleration. And from working with velocity time graphs, we know that we can find acceleration by calculating the gradient of a velocity time graph. So this connection between gradients and velocities and accelerations is what leads us to these two facts, that we should always state these facts in questions because they're usually worth the mark for stating the fact. We can find velocity by finding the gradient of a distance time graph, or displacement time graph, sorry. So that's one fact. And then the second is that we can find acceleration by working out the gradient of a velocity time graph. So these two facts are ones that we should state at the beginning of questions, and they will help us to solve the problems that we come across. So this is example 4 from the textbook. So example 4 says that we have a particle P moving on the x-axis at time t seconds. The displacement x from O, the origin, is given by t to the power of 4 minus 32t plus 12. And we are asked to firstly, in part A, find the velocity of P when t is 3. So for part A, we need to find the velocity of this particle when t is 3, and I denote that by a little subscript of 3 there. So we're going to use this fact here, that the velocity is the gradient, or the rate of change of displacement. So to get this velocity function, I'm going to do dx by dt, which is going to be 4t cubed subtract 32. And then to find the velocity when when t is 3, so at 3 seconds, we're just going to substitute in the number 3 into the function. So we end up with 76 meters per second as our answer. For part B, we're asked to find the value of t for which p is instantaneously at rest. So if we're at rest, then we're not moving, are we? We're stationary. And if we're not moving, and we're completely still, then our velocity is equal to 0. So to find the time when we're at rest, we're going to set this velocity function equal to 0, and we're going to find what time that is. So I'm going to have 0 equals 4t cubed subtract 32, and then this is quite a simple equation to solve. So at 2 seconds into the motion of the particle, it is at rest. It's not moving. And then part C, I'll do over here. For part C, we need to find the acceleration of p when t equals 1.5. So we're going to use this fact here that the acceleration is the rate of change of velocity. So I'm going to differentiate this velocity function that I have here, which will be 12t squared subtract 32. And then the acceleration of p when t is 1.5, so I need to find a of 1.5, and I'll just substitute that value in. To get 27 meters per second squared.